Hello students, welcome to EPG Pathshala. I am Dr. Varun Vyas from Department of Physics and Astrophysics, University of Delhi. Today we are going to talk on module Electrochemical Capacitance Voltage Technique under the paper Characterization of Materials 1. After completing this module, the students will be able to understand principles of ECV technique, the electrochemical cell, the carrier concentration measurements, measurement procedures, and characteristics of electrolytes. The realization of semiconducting devices for optimum performance and reliability requires precise knowledge of doping profiles. So, the measurement of dopant concentration and its correlation with the experimental parameters is crucial. There are various techniques like spreading resistance profile (SRP), stripping Hall profile (SHP), which give the additional information about the carrier mobility, capacitance voltage (CV). Additionally, the measurements of Schottky diodes have been used to enumerate the carrier concentrations. The standard SRP technique cannot be used to characterize junctions, that is, less than 100 nanometer deep. In addition, the application of proper sample preparation technique and probe conditioning in connection with an advanced analysis of the measured raw data is required in order to obtain the reliable results by SRP. SHP is rather time consuming and an intrinsic detection limit exists for low dopant concentrations. Due to reverse bias breakdown voltage and reverse leakage current, conventional CV profiling is limited to certain depth of Schottky diodes. It is crucial for evaluation of highly dopant semiconducting layers, which are almost present in all basic and advanced devices structures. The maximum depth that can be profiled restricted due to electrical breakdown for a certain distance that corresponds to a total space charge of about 2 into 10 raised to power 12 charge per centimeter square. Furthermore, the CV profiling of low bandgap materials and materials like INP is difficult. The electrochemical capacitance voltage technique was employed to measure the active carrier concentration profiles in semiconducting layers. ECV is a common characterization method to investigate the doping profiles of semiconductor layers by a depth-based CV measurement by varying the conditions at semiconductor electrode interface, resulting in controlled etching of the material. The ECV method uses semiconductor electrode Schottky contact to create a depletion region. Depletion region is the region containing immobilized ionized charges such as ions, which are electrically active, defects, or traps. Due to the presence of ionized charge, the depletion region behaves as a capacitor. Capacitance measurements give an idea about the dopant and electrically active defect densities. Depth profiling is realized by etching the semiconductor electrolytically between the successive capacitance measurements. Principle of ECV technique. ECV profiling involves two basic steps. A. Determination of carrier concentrations by measuring differential capacitance of the Schottky barrier produced at electrolyte semiconductor interface, and B. Controlled removal of material via electrochemical anodic dissolution. Both steps are repeated to obtain variations in the carrier concentration with depth. In case of p-type semiconductor, the flow of the holes due to the forward biased barrier effect, the dissolution reaction, whereas the holes in the reverse bias promote dissolution process in n-type semiconductor. These holes in n-type semiconductor can be degenerated optically by illuminating with blue light. These electrons are absorbed near the surface of the semiconductor, thereby promoting dissolution. Typical dissolution rate are around 1 micrometer per hour. The thickness of removed material is calculating by taking integration of dissolution current and applying Faraday's law. Actual depth can be determined by adding this thickness of the local depletion depth. Electrochemical cell. Figure 1 shows the schematic of an electrochemical cell. Sample is pressed against a sealing ring in the electrochemical cell with electrolyte. Contact area can be controlled by the size of the ring opening. By applying a potential between the platinum electrode and semiconductor, depletion region is formed and measured with respect to the reference, that is standard calomel electrode. The varying current between the semiconductor and the counter electrode can regulate etching conditions. Carrier concentration measurement. Depending on the charges of the ions that are present at the interface, carriers can accumulate, attracted, or deplete, repelled in the field affected region. For determining the carrier concentration through 3V technique, conditions should be favorable for the formation of depletion region. In p-type semiconductors, holes are majority carriers. Thus, positive ions must be present in the solution, which is given in figure 2. By making semiconductor more negative, that is doped by pentavalent impurities, than its equilibrium value, positive ions are drawn towards the interface and holes are pushed back. In n-type semiconductor, electrons form the majority charge carriers and therefore negative ions are needed. So, semiconductor needs to be more positive than its equilibrium value as shown in figure 2. If the electrolyte is concentrated, normally greater than 0.1 molar, the semiconductor electrolyte interface acts as a Schottky junction. The potential drop across the Helmholtz layer is constant and surplus applied potential drops across the depletion layer. Thus, the normal metal semiconductor theory applies to this junction, and the depletion width WD is given by WD is equals to square root of 2 into phi minus V into epsilon naught into epsilon r divided by En, where the phi is the built-in contact potential, N is the carrying concentration, E naught is the permittivity of free space, Er is the relative permeability of the semiconductor, and A is the effective contact or H area. From metal semiconductor junction equations, there exists a linear relationship between 1 by C square and V, with C the junction capacitance and V the applied voltage. Here 1 by C square is equals to 2 into in brackets phi minus V. This whole is divided by Q n into epsilon naught into epsilon r into A square. Here Q is equals to charge of the electron. At the edge of the depletion junction, the charge carrier density becomes N is equals to 1 by Q into epsilon naught into epsilon r into a square. This whole is multiplied by C cube divided by dc by dv. Hence, N can be calculated by measuring dc by dv, A and C. Parameters dc by dv and C can be determined directly from a slowly modulated high frequency voltage. A area should be computed accurately. Etching conditions. Etching conditions. Depth profiling is performed by electrolytical dissolution or etching of semiconductor. Dissolution increases the separation of electric charge carrier due to the presence of holes. In p-type semiconductors, holes form the majority carriers, and dissolution is easily done by applying forward bias to semiconductor electrolyte junction. And in n-type materials, holes may be created by either elimination or applying reverse bias to the junction. Even a short wavelength light can promote electrons to conduction band from valence band, leaving holes behind which are drawn towards the surface by reverse biasing the junction. Figure 3. The wavelength lambda must satisfy the condition lambda that is smaller than Hc divided by Eg. The dissolved H depth, that is Wr, varies with the dissolution current I according to the Faraday's laws of electrolysis. The Wr is equals to m divided by Z F rho A multiplied with the integral of dissolution current I into dt. Here m is the molecular weight of the conductor, Z is the dissolution valency, that is number of charge carriers spent in the dissolving single semiconductor atom, F is the Faraday's constant, rho is the semiconductor density, and A is the contact area. The measurement depth of the carrier density is given by W is equals to WD plus WR. Measurement procedure. First, plot IV characteristics to obtain voltage range for the measurement of capacitance and potential required to initial etching. This is shown in figure 4. Second, perform CV analysis to get measurement potential shown in figure 5. 3. From the above calculated values, carry out depth profiling. Performance specifications in R carrier concentration, that is 10 raised to power 13 to 10 raised to minus 20 per centimeter. Depth limit is between 0.05 to 50 micrometer. Depth resolution is 1 nanometer. Carrier frequency is between 0.3 to 25 kilohertz, and the modulation frequency is between 0.01 to 2.55 kilohertz. The accuracy of all carrier concentration profiles obtained from the measurement of mod Schottky capacitance characteristics depend critically on the area of semiconductor contact and its edge definition. Special care is needed to measure the area of the electrolyte in contact. For n-type semiconductors, in practice, the limits of the wetted area may extend somewhat beyond these of the illuminated area. The difference is termed as an excess area and needs to be taken into account for accurate profiling. Since dissolution restricted to the illuminated zone, whereas the whole wetted area contributes to the capacitance measurement. Hence, the excess area wetted by the electrolyte but not electrochemically etched must exactly be determined as well. Furthermore, for heavily doped material or near a p-n junction, a series of resistance may influence the profile determination. Schottky diode includes a junction capacitance C, a junction conductance G, and a series resistance Rs, depicted in Figure 6a. The conductance determines the leakage current across the junction. The series resistance depend upon the resistivity of the bulk wafer and on the contact resistance. Capacitance meters assume the device to be presented by the parallel circuit in Figure 6b, where Gm and Cm are measured conductance and capacitance respectively. Comparing the two circuits and considering only the capacitance factor, the measured capacitance Cm of a junction device is related to the actual capacitance C as Cm is equals to C divided by in brackets 1 plus Rs G whole squared plus in brackets 2 pi omega Rs C. This is also whole squared, where omega is the measurement frequency. For the measured capacitance to be approximately equal to the actual capacitance, it is necessary that Rsg is much smaller than 1 and 2 pi omega Rsc whole squared is much smaller than 1. Hence, the series resistance should be as negligible as possible. The Rsg is much smaller than 1. Requirement is usually met by junctions with reasonably low leakage current. Conducting layers on semi-insulating substrates particularly suffers from series resistance effects. These measurements are met most readily using diodes of large area, since this increases the value of C and decreases the series resistance and reduces the fractional error in area. ECV profiling may suffer from an inaccurate definition of the etch depth if the chemistry of the material removal is complex. For example, during anodic etching of Si in an electrolyte containing hydrofluoric acid, the effective dissolution will in Z, that is, number of holes required to dissolve one silicon atom, is heavily affected by its concentration. The dopant type and the concentration type, the electrode potential, and illumination intensity for homogeneously doped material and optimized for Z is equals to 3.7 plus minus 0.1. Characteristics of electrolytes. Key to the successful profiling is the choice of electrolyte. Accuracy of carrier concentration is basically influenced by factors profiling, series resistance, and accurate calculation of the contact area of the electrolyte. Calculation of N into Xt from Ac divided by Av requires electrolyte semiconductor contacts like a Schottky diode with a barrier height which is not voltage dependent, and accurate measurement of C requires the electrolyte resistance is small compared with 1 by omega C. The resistance values of some electrolyte being studied is enumerated in Table 1. In Table 1, resistance values and free H rates of different electrolytes are given. In table, we have different electrolytes made up of nitric acid, phosphoric acid, and hydrochloric acid. Resistance of electrolyte solution is given in column 2 and free chemical etch rate is given in column 3. The chemical etching rate is very low in comparison to the rate of anodic dissolution under dark conditions. The effects of series of resistance can be minimized by dissipation factor or D factor. The D factor can be obtained by taking inverse of quality factor Q of the model circuit of electrolyte semiconductor interface. The lower D factor, the lesser is the effect of the series resistance. As seen from the table 1, the electrolyte 2 has a minimum free chemical H rate and considerable low resistance. Table 2 enumerates the ECV profiling of N-type semiconductor material. The parameters included in the different columns can be used to select most suitable electrolyte for different experimental conditions. For table 2, D is the dissipation factor and Q is the inverse quality factor of the model circuit of electrolyte semiconductor interface. Phi B is the barrier height of the electrolyte semiconductor junction. The electrolyte 2, that is from table 1, is found to have extremely low D factor values, thereby indicating that the effect of series resistance are insignificant. In addition to this, the barrier height of the electrolyte 2 is also reasonably like the traditional electrolyte, that is HCl. This makes electrolyte 2 best suited for ECV profiling. Accurate measurements of edge depth and capacitance requires that the diode area is well defined with minimum or no leakage of electrolyte under the sealing ring. The contact area definition is most critical. The accuracy of both carrier concentration results and the edge depth depends on the correct estimation of the contact area. Hence, the accurate physical confinement of the electrolyte by sealing ring without outflow is important. The contact area is usually defined as the plastic sealing ring calibrated against a blue slice sample and assured by repeated calibration. The blue slice is a piece of polished N-type gallium arsenide substrate that has been anodized to grow an approximately 50 nanometer thick anode. This oxide is blue in color and thus gives the sample its name. The calibration has been performed by profiling the blue slice sample and then measuring the wetted and illuminated areas in a microscope. Illuminated areas are clearly visible as N-type material etches in light, although wetted areas does not usually etch with N-type material. It is clearly visible with a blue slice run. Thus, blue anodic oxide is chemically removed from the electrolyte. In addition to this, electrolyte 2 doesn't create any rounding of the creator edge, that is, enhanced etching at crystal edges is minimum, as evident from optical microscope image of the edged creator and stylus. Surface profiling after the ECV measurements is included in figure 7a and b respectively. As seen in the figure, with well sealing ring, the electrolyte creates a sharp creator wall and a flat creator bottom. That is, a lateral etching is uniform. Moreover, the dissolution number of the electrolyte was found constant. Here you can see in figure 7a is the optical micrograph whose magnification is equals to 1.5x of the creator after ECV profiling, and B, you can see the techno stylus profile of the creator after ECV profiling was used using the proposed electrolyte. So students, let us now summarize what we have studied in this module. In this module, we studied about the electrochemical capacitance voltage technique, that is ECV technique, which is employed to measure the active carry concentration profiles in semiconducting layers. We looked into principle and the design of an electrochemical cell, and the measurement procedure and its limitation were examined in detail. In the end, we looked into the characteristics of electrolyte and how various types of electrolyte affect the accurate measurement of carrier concentrations between the layers. Thank you.